Welcome to the second PV3x summary video. In the first part, we discussed location issues and the PV modules. Now we'll continue with the balance of systems. As we learned during week 4, the maximum power point of a PV module is constantly changing with temperature and irradiance. Therefore, the maximum power point must be tracked to maximize the energy output of a solar module. In theory, this could be done with a variable resistor. In practice, maximum power point tracking is implemented to control the switches in a DC-DC converter. The DC-DC converter also allows to decouple the voltage of the PV module from the load voltage. Maximum power point tracking algorithms can be classified into indirect methods, which do not require measuring the IV curve of the modules, and direct methods, which require to measure the IV curve to find the maximum power point of the solar panel. Direct methods are generally more effectively because they can dynamically track the changes in the IV curve. The two most common direct maximum power point tracking methods are the Perturb and Observe and the Incremental conductance. The Perturb and Observe method applies voltage perturbations at the input of the DC-DC converter to find the maximum power point. The sign of the voltage perturbation in each iteration of the method depends on the change in the power obtained from the previous iteration. A disadvantage of this method is that it oscillates around the maximum power point. The incremental conductance method considers that at the maximum power point, the derivative of the power with respect to the voltage is zero. The sign of the voltage step in this case depends on whether the operation point of the modules is on the left or on the right side of the maximum power point. In a PV system, maximum power point tracking is usually implemented in the charge controller or in the solar inverter. Both devices contain at least one DC-DC conversion stage, which is needed to step up or down the voltage of the PV modules. Charge controllers are used in PV systems with storage, and they regulate the charging and discharging process of the battery. Inverters are needed to power AC loads and when we want to connect the PV system to the grid. In PV3x, we discussed three main types of DC-DC converters. The buck converter, which allows to step down the voltage of a PV module, for example, to charge a battery. The boost converter, which allows to step up the voltage of a PV module. And the buck boost converter, which can either step up or down the voltage of a PV module. Boost and buck boost converter usually constitute the first power conversion stage of solar inverter. The efficiency of a DC-DC converter can be determined from the output power and the power dissipated in the electrical components of the converter. The dissipated power takes into account conduction losses in switches and diodes of the circuit, the conduction losses in the coil, and also other sources like switching losses. In this course, we only studied how to calculate conduction losses. The efficiency of an inverter is more complicated to calculate. One way of expressing the efficiency of an inverter is with the Sandia National Lab SNL model, which uses a series of empirical coefficients to determine the inverter efficiency as a function of the input voltage and power. Power converters and PV modules can be arranged in different configurations according to the system's requirements. Each of these different system topologies pose advantages and disadvantages in terms of efficiency, rated power, flexibility, and cost. Finally, we learned about different types of grounding-related issues, including potential induced degradation, TCO corrosion, and islanding. The characteristics of the inverter are important to avoid or mitigate these issues. Hence, this should be taken into consideration at the time of selecting the appropriate inverter for a system. This concludes the second part of the PV3x summary video. In the next part we will continue with the AC yield calculation and financial aspects.